a family of stochastic charge scales model. Okay, this pointer doesn't quite work. So, to me, there are two good reasons to be interested in this kind of models. The first one is that these models are known to show something called anomalous fluctuations. So, if you look at their hydrodynamic fluctuations, I will give you the definition of what I mean by hydrodynamic fluctuations in a moment, but I just want to say that in anomalous fluctuations, these so-called hydrodynamic fluctuations are known to show really peculiar behaviors. And although in recent years these anomalous fluctuations have been studied in the context of mainly in the Hamiltonian dynamics, for example, Heisenberg spin chain, for example. But these models are also known to show such anomalous fluctuations, and these are kind of easier to handle analytically, so we can learn a great deal about the basic physics of anomalous fluctuations by looking at these kind of models. For anomalous fluctuations that are shown by the kind of systems that have these two symmetric charges. But there is also another reason why these models are interesting, and that's the kind of point that I want to emphasize more in this talk. So the reason is these models are also known to be linearly degenerate. So again, I'm sorry for throwing so many jargons at you, and I will define what I mean by these words when the right moment comes. But linearly degenerate basically means that the system is kind of as close to integrable systems as possible, but not be integrable. So these models are actually, they happen to be such linearly degenerate systems. And their hydrodynamic fluctuations have been, I mean, to my knowledge, not quite explored. So that's the kind of main objective of this project. And we found something interesting in the hydrodynamic fluctuations in these systems. So these are the kind of systems that are an example of linearly degenerate systems. So that's the kind of thing I want to talk about in this talk. Okay, so, right. But let me start with something really basic and to motivate why I think these fluctuations are interesting. So the kind of fluctuations I want to talk about are something called current fluctuations in many-body systems. And here, many-body systems can be really any systems, could be quantum, classical, or deterministic, or even stochastic, so long as there are some particles that are interacting non-trivially in the system. And now we can consider some simple setup just to illustrate the kind of fluctuations I'm interested in. So suppose your system is in some statistical ensemble, for example, some thermal equilibrium, or could be even in a local equilibrium. And now what you want to do is to compute the number of particles that pass some certain position in the space, for example, the origin, for a given period of time. And if you make such a measurement, every time you do it, you get a slightly different number. And the reason is obviously because the system is in ensemble, statistical ensemble. So the number is going to fluctuate. But the way the number you get every time is fluctuating is not entirely arbitrary. So the number is fluctuating around the mean value of the current, and there's a probability distribution that characterizes such distribution of such numbers. So that's what I'm after here. And this kind of studies sometimes also for counting statistics in the context of condensed matter theory. And I think traditionally people have studied this kind of statistics in the context of transport in mesoscopic systems, in particular electron transport in mesoscopic systems. You can, for example, prepare this kind of 2D material where you have some voltage imbalance in the system. There's a gate and across which some electron current is passing, and you can ask what would be the statistics of such a current. And the experimental people really could observe not just the mean value or the variance, but also kurtosis and in general higher cumulants of the current. So that, okay, this is the definition of the this is the time-integrated current, which can be also written as like this, where the rho is the particle density at position x and time t. So that's the kind of status quo of the full-counting statistics. But in general, you don't have to confine yourself in such systems and mesoscopic systems, but you can ask the same kind of question: what would be the statistics of the transport in your system? And it's of course difficult to say something quite general about such statistics in a generic system, but there is a nice theory that allows you to evaluate such statistics. So, and the theory is called macroscopic fluctuation theory. So I will use a kind of theory that is inspired from this theory, and I will give you a bit more technical details of it. But basically, this theory is based on hydrodynamics, and it really allows you to calculate these fluctuations based on hydrodynamic data. For example, if you are interested in the large deviation of the current, so by large deviation, what I mean is that the current or the transferred particles you observe could be sometimes significantly deviating from the mean value. And that kind of event is called rare event. And if you just focus on such a rare event, there's the probability distribution of such rare events is actually known to follow something called large deviation principle. And that kind of distribution can actually be nicely captured by looking at this generating function of the time-integrated current. So this is just an average with respect to some initial condition, which I am going to take with respect to, I will take usual thermal equilibrium as an initial condition in this talk, but it can be some other initial condition as well. And under this assumption that large deviation principles is going to behave sympathetically like this large T, where alpha is dependent on the underlying transport type. For example, if you're dealing with some system that shows purely diffusive transport, like in non-integrable spin chains, then this is just going to be 1/2. Whereas if you deal with some continuum systems, then this is going to be usually just linear time. So alpha is 1. And this f of lambda is something called scaled cumulative generating function, and I'm going to compute this for the models that I mentioned in the previous slide. But I'm going to do much more than that. All right, and this kind of study, MFT has been applied to many systems, from stochastic exclusion processes to more recently many-body systems, quantum many-body systems. But I didn't really cite these papers I'm sorry if there are people in the audience who worked on this theory before. I'm just saying that there are many good works applying this MFT. I just wanted to emphasize before moving to the next slide that the prediction of the MFT has been recently verified by a nice experiment. This one using so-called quantum simulators. It's the experience of the motion of individual atoms precisely, and they could really show that MFT prediction is pretty accurate even for full-fledged quantum many-body systems. So the study of these large fluctuations and in general full-counting statistics in generic quantum many-body systems has been pretty popular these days. All right, so that's the kind of background. And although I'm going to talk about somewhat exceptional systems, let me just quickly brief what are the general expectations for non-integrable systems, non-integrable many-body systems in all dimensions. I'm focusing on here in one dimension because in all dimensions, the fluctuations are usually richer and there are more varieties. So in this talk, I will just focus on the one-dimensional cases. You can loosely divide systems, many-body systems, into two categories. The first one is spin chains. For example, you can consider XYZ chain in a magnetic field as a kind of example non-integrable spin chain, which just conserves the energy. There are no other conserved charges. So for that energy, you can write down the hydrodynamic equation. If you want to include the fluctuation around the mean value, then you can write down this kind of fluctuating hydrodynamics. So that's the usual thing. And instead, if you want to know the large fluctuations, the rare events, then you can use, like I said, so-called the macroscopic fluctuation theory, and this is the kind of prediction. All right. Now, we can also look at continuum models, continuum non-integrable models, and these models have been also explored quite extensively. For example, you can take aharmonic chains or Fermi-Pastor-Lamb chains if you, as an example system for non-integrable continuum models. These models look like this, where V is some potential that is not harmonic. And these models have been also studied hydrodynamically, famously by Harvard, and but it's quite different from the usual fluctuating hydrodynamics. It has to be taking this form. The reason is that numerically, at least, you can convince yourself that diffusion constants of these models are divergent. So the things are not, transport is not quite diffusive and, well, basically super diffusive. So you have to do something a bit more than fluctuating hydrodynamics. And the answer turns out to be to just include this expansion of the current up to the quadratic order, not just the first order. And by just putting the noise here, white noise, you can have a hydrodynamic theory for such transport in continuum Hamiltonian models, non-integrable Hamiltonian models. And by doing something called model coupling theory, you can show that these transports really show what some transport would show. For example, KPZ behavior. Some transport might be described by a bit more exotic transport type, for example, Levy flight. So, but that's something that people have really understood pretty well in the last 10 years. So this is quite different from the spin chain case, but when it comes to large fluctuations, there's more similarity between these two models. The only difference being that the exponent here is not going to be square root. Shouldn't touch probably, but just linear in time. And this is because the underlying transport in these systems are ballistic. I mean, if you forget about these ballistic corrections, this is just an Euler hydrodynamic equation which is ballistic. So that's why you have this behavior. Okay. So that's the general expectation.
No, but wait, but the ballistic MFT is not correct in the case of nonlinear fluctuating dynamics, right?
Where do you say that?
Is it?
It's for large fluctuations.
Okay.
I'm not talking about typical fluctuations.
Can I ask about what goes in the f of lambda? So I guess you have closed form expressions for f of lambda. What does it depend on? It depends on
it's just a function of this counting field lambda, and it really depends on the model you're looking at.
So, but the data, so it presumably just depends on, let's say on the left, on the diffusion as a function of density? Or does it?
Yeah, but it depends on some, I mean, the model parameter. I mean, it's not, because this diffusion constant, okay, this is written as a linear hydrodynamic equation, but when you use, for example, this kind of hydrodynamic equation in the MFT, it has to be promoted to the function of densities.
Yeah.
So,
but it doesn't depend on more than diffusion constant as a function of density and susceptibility as a function of density.
No, okay, that you're right. Essentially, this really depends only on hydrodynamic data. So yes, like diffusion constant.
And initial state, right? And that's it.
And yes, and initial state, of course. So these are the kind of, I mean, I will explain the main philosophy of MFT or BMFT later. So, okay, let's say BMFT. So BMFT means ballistic MFT. So it's just a straightforward generalization of the macroscopic fluctuation theories. Because this is like I've been repeatedly saying, this is for diffusive transport, whereas this ballistic version is for the for systems that support ballistic transport. So looking at different kind of systems. All right. So for integrable systems, you have you can again categorize systems into these two categories, but they in fact do not really behave differently, and they behave more or less similarly, whether they are spin chains or continuum models. And the reason is because they, either way, they have a number of concept charges. So they have this ballistically propagating modes, like Jacopo was saying, and as a result, you're going to have always ballistic transport, except some certain situations. And for example, for the spin chains, you have this kind of XYZ chain as a representative model, whereas for the continuum case, you have the linear model. Right.
And so this ballistic MFT, you're proposing it only for integrable systems or even for things like FPU?
No, I would say ballistic MFT is going to work for any systems whose largest scale transport is controlled by order transport.
But for like FPU, I mean, even though like correlations have anomalous scaling and so on, it's not ballistic, right?
I mean, the ballistic scale, they are not important. So only thing that matters at ballistic scale is that there are these convective contributions and they control the large deviations.
Maybe one thing to say is that the BMFT actually assumes uniqueness of solution to the early equation, which is not correct if you have shocks. That's the
yeah, before the shocks, but yes, that's true. Thank you for the remark.
But the scaling is correct.
Yeah. All right. Now, you can also do hydrodynamics, as Jacopo explained very well, and this is called generalized hydrodynamics. And yeah, up to diffusive correction, this is the right form. I mean, it's not too different from the usual case, but as explained, if your initial condition is local equilibrium, actually this diffusion correction is not the right form, but it looks somewhat a bit more complicated. But so long as we deal with a situation that is close to equilibrium, for example, in a linear response regime, this is pretty good. So that's the kind of GHD up to diffusive corrections. And again, for the large fluctuations, you can use the ballistic MFT to describe, to calculate this function f of lambda. So that's a kind of situation for integrable systems. Now, let me say a few words about the nature of diffusion and all that Jacopo already explained, and also its relation to linear degeneracy. So the first comment I want to make is that there's no normal diffusion in integral systems. And the reason is simply because there are no fast modes that would constantly kick around the slow modes that amount to some jiggling behavior of the slow mode. For example, in non-integrable spin chain, you're having basically the energy transport, which is undergoing a suite of fast modes, and that's why you have to put these white noise, which is accounting for such fast modes. But there's no such thing in integrable systems. What happens is that in integral systems, you have an infinite number of concept charges which amount to these stable quasi-particles that carry these hydrodynamic fluctuations without really dissipating any fluctuations. So what happens essentially in integral systems is that fluctuations are carried by these quasi-particles, and fluctuations are really just coming from the initial condition. And that's what we call diffusion from convection in integral systems. And that's the source of diffusion in these systems, which is in stark contrast to non-integrable systems. So this is a kind of cartoon of what's happening here. So what you have to do really is to prepare initial fluctuations at the scale you're looking at. For example, could be in Euler scale, or could be diffusive scale, and you have to propagate with the Euler equation like this. Here A is what we call Fox Jacobian, which is defined in this way. But you can also move to so-called normal modes by going through some nonlinear transformation, and you can write this equation like that, which could be a bit nicer because then each mode has its own unique velocity like this. Now, this is also a nicer form of for my purpose because if you write in terms of normal modes, then you can say that self-interaction, which means that the velocity of the mode itself, depending on the density of the mode, is going to be present in generic systems. And that is why this can also be written as like a G function, and G function is basically related to this Hessian here. So if this is non-zero, then they generically have this kind of quadratic contribution, and this induces super diffusive behavior. And this is precisely what is absent in integral systems. So this sets the kind of, gives the definition of the so-called linearly degenerate systems. So for linear degenerate systems, you have no self-interactions, meaning that this kind of condition is true for every I. So in that case, you kind of avoid having super diffusion, and as a result, the systems can really have both diffusion from convection and also normal diffusion. So linear degenerate systems are kind of slightly more general than integral systems, in the sense that you can also have this normal diffusion. But at the level of the Euler hydrodynamics, they're pretty similar. So that's the kind of illustration here. I'm interested in the hydrodynamics of linear degenerate systems, where the definition is this, and I want to, in particular, characterize the fluctuations of such systems. Okay, so it's kind of slightly more general than the fluctuations in integral systems. But I will start with integrable case by looking at this example. So I wouldn't deal with a proper minimally interacting integral systems like Jacopo did, but I will look at something a bit more, something simpler. So these models are cellular automata, and they are charged, and they can be also stochastic. But I will occasionally turn off the stochasticity just to make the system really deterministic and also integrable. Anyway, so here's the definition. So these models are defined on a lattice of size L. At every side, you can have three different states: the vacancy, the negative charge, or positive charge. And by gathering all these states at every side, you can have a string of states, and that would give you the state at a given time t. Okay, so this is the state. Now, the way to derive the dynamics is to apply this kind of two-body map at every neighboring site. So for two neighboring sites, states, for example, you can apply like this, and the rule is also pretty simple. So the first rule says that if two neighboring sites happen to accommodate just the vacancies, then of course there's nothing happening. Whereas if you have one vacancy on one side and some kind of charge on another side, then they're going to swap. The last condition is a bit more complicated. What happens is if two sides happen to have some kind of charges that are different, then they will swap their charges with a probability gamma, or otherwise they remain the same position with a probability 1 minus gamma. So this means that if you tune gamma to 0, then the system is fully deterministic, and there's only hardcore interaction among charges in the system. And that kind of limit is fairly useful, so I'm going to take it at some point. But anyway, now we can just keep this gamma generic, and the full dynamics is governed by the breakwork circuit, which can be obtained by putting these maps in this breakwork fashion. So this is the kind of full dynamics, and yeah, that's it really. That's the definition of the model and the dynamics. And these models are so simple that they can be solved analytically, microscopically, which have been done in these papers. And they are known to show some so-called anomalous fluctuations. Yeah. All right. So this is the model.
Is the model? Does it mean that the model is integrable?
Yes, I'll come to that. Well, it's not too obvious actually, but to my knowledge, it's not proved yet. But we believe this is integrable. It's actually more than being integrable. It's something called, sometimes people call this super integrable. So it's not just having extensive number of charges, but also has an exponentially large number of charges.
But you don't have, Yang-Baxter relation.
Yeah, I mean, I think that there are such structures. It's just that people haven't, well, maybe people have done, but at least I don't know such work. Yeah. So, but yes, this model is supposed to be integrable, but it's not just an extensive number of charges, but exponentially large number of charges. But the point I want to make is that these really large number of charges are not going to be mostly important, but there are only 3 physically relevant charges. So the first one is a total charge, because it's a charge conserving system. And then there are left and right movers. So if you look at this kind of trajectory for given initial condition, you immediately see that the number of right moving charges is conserved, right? And they, once they are propagating like this, they are always on the same kind of trajectory. And if you follow the trajectory, you can just be a colorblind because you're just forgetting about the charge, but looking at the whether the particle is present or not in the trajectory. And you can see that these so the trajectories are always on this side. And the same for the left movers. The number of left movers is also conserved. So we have 3 conserved quantities, physical quantity charges in the system. And you can forget about other charges. And the reason why we can forget about other charges is that if your initial condition has just is thermalized with respect to these charges only, then we can show that the dynamics is going to be self-contained in the sense that the dynamics of these charges needs to know only the dynamics of just their charges themselves. So they will time evolve. They're referring to the dynamics of other charges, provided that you start out with initial condition that is including just these 3 charges. So that's what I'm going to do. And I will, so that when I do thermodynamics, I will prepare the initial Gibson symbol like this. So this is my JGE. And with that, we can, for example, calculate the densities of these GG averages of these left movers or the total charge in this way. It's not important to remember these expressions. It's just that you probably have to. It's better to remember what B is and how B is defined here. So B is a Haber tangent of the B to C, where B to C is the Lagrange multiplier of the total charge. And B is going to control how charged your system is, meaning that if B is 0, then it means that the system is at half filling or the charge neutral. But in general, B is not going to be just strictly 0. So this B is going to tell you how charged your system is.
So sorry, maybe I want to make sure about the model.
Oh, yes.
So the 2 cases with gamma and gamma bar, so are they complementary cases?
So yeah, this
gamma plus gamma bar, is it equal to 1?
Yeah, exactly. Yes.
Okay.
Yeah, this is just these 2 panels are describing these 2 issues.
Gamma bar is just a 1 minus gamma here.
Correct.
Okay.
Yeah. Sorry, I didn't define. Yes. So thank you for pointing that out.
One can think about also the special cases where gamma is equal to 0 or 1, right?
Correct. And I would take gamma equals 0 limit.
So they become deterministic?
Deterministic, yes.
Oh.
Yeah.
Is it kind of singular, or you can still apply kind of general theory?
Yeah. Well, it's a single limit in a certain sense, but I can basically apply what I'm going to tell you for any value of gamma.
Thank you.
All right, so now let's talk about hydrodynamics. So this is my all hydrodynamics for the system, where a matrix here is now given in this way, which you can compute easily. And now you immediately see that these three-mode hydro equations are closed. Oil equations are closed and independent of gamma. So the first two equations are super simple. They're just saying that these left and right universes are traveling diagonally along the light cone in the system, whereas the third equation is telling you how the charge is going to evolve in time hydrodynamically. And this is somewhat non-trivial because now the velocity is dependent on the state. But the way it depends on, this velocity itself turns out not depend on the charge. So this property is sometimes called charge inertness, and this makes the system also linearly degenerate because all these velocities are not dependent on their own densities. To claim that you have to go to normal mode, but you can immediately see that. So, and this B field that I defined earlier, like this, turns out to be also a normal mode, a good choice of normal mode. So I'm going to use this equation also. So you have now three modes, right? Three hydrodynamic modes, and also you can write normal modes for these three modes, and each mode has either +1, a velocity +1 or -1, or some non-trivial velocity between -1 and 1. So these are the kind of velocities of the charges now. And actually, there is so kind of three-mode hydrodynamic equations that are similar to this. Were also found for the Dirac fluid in the paper by Salan and Roma. But this is derived from the microscopic information that you can get.
One question. So as I asked, this model seems to be integrable, right? Don't you have to use generalized hydrodynamics?
Yeah, good question. Yes, but yeah, the nice thing about this model is that, okay, one condition, important condition, is that your initial GGE doesn't contain any other charges, but only 3 charges. If your initial condition satisfies that condition, then the dynamics is self-contained, and you don't have to refer to the dynamics of other charges. But you're completely right that if your initial condition has all sorts of charges, then yes, you have to do GGE. Although I still expect some kind of simplification even in that case.
So is this then a three-mode GHD equation? Is that equivalent to this?
I don't think so, no, because
Why not?
Of course it is.
yeah.
The first two equations they are. The last equation.
Okay, yes, in a sense it's a
That's the.
yes. I don't know. Does it have this form of?
Form of quasi-particle.
I think you can, yes. Yeah, regard it as a GH2, but yeah, that's right.
Then you have a two-body scattering phase for these modes.
Yes, you can also write in that way, but yeah, this is simple enough that you don't have to.
Takato, when you say the equations are closed, right? If you just assume these 3 conserved quantities to be there, if you just assume your system to have n conserved quantities, you write down n hydro equations, they're always closed, just by construction, right?
Yeah.
So in order to check that they are closed, you need to add more conserved quantities and then see that they are decoupled, right?
No, but why do you have to do it? If you write it like that, it's clear that they are self-contained. Maybe other charges, time evolution also depend on the density of these guys, but if you just look at, for example, the charge densities, time evolution, then this is.
So you derive these from microscopics? Or?
Yeah.
Okay.
It's really coming from microscopics. So, all right. So this is the hydro equation, and in equilibrium, you can kind of observe that if the system is away from half-filling, then this is still ballistic. Charge transport is ballistic. But if you're at half-filling, then this is going to be diffusive. Actually, it's not kind of obvious whether it's diffusive. You can show that this A matrix is due to vanish, meaning that the ballistic contribution is going to be absent, but it doesn't mean that the substochastic contribution is diffusive. So this is a kind of information you have to put from microscopics. I mean, we know that from microscopic calculation, this transport is going to be diffusive, so have to use this fact that this dynamic exponent is going to be equal to. Anyway, so the situation here is very similar to the spin transport in Heisenberg spin chain in the z-axis regime. So yeah, the resemblance is quite, it is there.
So sorry to make sure. So what is the similarity? So diffusive case corresponds to delta bigger than
Yeah, I
1.
mean this kind of situation, meaning that at half filling also in the z-axis Heisenberg chain, you have a pure diffuse transport for the spin.
Delta bigger than 1.
Yes.
Whereas P non-zero corresponds to delta less than 1.
No, it means that it's not at half filling. I mean, it's a charge, the system is charged. It has a manipulation.
Okay, thank you.
All right, so now I want to do first I want to understand large fluctuations in these models. Although this is not the kind of fluctuation I want to focus on, and I will look at the typical fluctuation later, but just to give you a flavor of how BMFT works, I will look into large fluctuations. So the object of interest is now this generating function, and like I said, what I mean by large fluctuations is that the current is fluctuating on this order, which means that large deviation principle is going to tell you the probability distribution is having this form, where I of j is something called rate function. Now, this is in general hard to compute, so what people typically compute is something called scale cumulative generating function, f of lambda, which is defined in this way. And this guy is related to the rate function in this theory, this Legendre transformation. One thing that is peculiar in these models is that cumulants cannot be obtained by just taking the derivative of this scaled cumulative generating function, and simply because of the presence of anomalous fluctuations. So this kind of scaled cumulant turns out to be divergent in time. So that's one kind of unusual reason. Usually this kind of these cumulants defined, I mean, given by taking derivatives of this f of lambda are expected to be finite in time. All right, I will observe that a bit more precisely later. Okay, so here is the important theory. So the theory I'm going to use is called the BMFT, ballistic MFT. And although I wouldn't give you the full details, but the main principle of this theory is very simple. So it's telling you that in integrable systems, or in general in any many-body systems that have ballistic transport, the only large fluctuations that contribute to these large fluctuations at a later time are coming from the initial conditions. So what you have to do is to feed the initial conditions properly in this theory and try to propagate these initial conditions using the order hydrodynamics. So and let me explain how one can implement that kind of idea. So you start with these hydrodynamic density fields. So these are the kind of important fields that I'm going to integrate my path integral over with. So I take this microscopic density and I will scale these coordinates like this, and this is my density. Okay, but these are still fluctuating, so these are not like a fixed number. Now, like I said, you have to prepare your initial fluctuations. So the way you do it is just to use the result, which actually, I mean, you can reproduce it very easily, but also has been known for a while. And this density probability distribution at this scale is known to take this form, large deviation form, where this curly f is something called large deviation function. And here small f is something called free energy density. So this is what you usually find in the business of MFT also. Now, another constraint is that these fluctuations are now propagated by the order operation. So that's something you have to also implement by putting the delta function in the path integral over these fields. So this is the constraint you're going to have to put. And for convenience, I'm going to write this using the Laplace transform like that. So these two conditions are important. And in BMFT, the claim is that there is no additional source of fluctuation in computing these large fluctuation objects. So this is quite different from the usual MFT, where you also have a dynamically generated noise, which you put in the equation as a fluctuating hydrodynamic equation, but you don't have to do it here. So this is the kind of setup for the BMFT. Now you have to just plug these pieces into this path integral formula. So the first one is just the current, which I'm interested in evaluating here, and then this is the initial condition, and now you have to ensure that the initial fluctuations are propagated by the hydrodynamic Euler equation, and you rewrite everything in this way. The functional S is something we call the BMFT functional. Anyway, the important point here is that although this path integral looks somewhat nasty, you end up with this kind of form, which is exponential. I mean, integrand is going to be something like exponential of tau times something, meaning that, indicating that at large tau, the only kind of contribution to this path integral comes from the saddle point. And that's, this large time limit is precisely the kind of limit I'm interested in here. So this is good news. You don't have to work out the full path integral, but you just need to look at saddle point. So you have to take the variation of this action with respect to the rho and h, and you end up with these BMFT equations.
Yes, good question. So in regular hydrodynamics, I guess you could hope to go beyond and have both, Euler scale and the diffusive broadening of sound modes. Is this something that has been done? Some kind of augmented? Yeah, let's say like viscous, corrections to.
I mean, for the usual case, you do have to put that but I mean, I think in the standard MFT, sorry, not BMFT, but MFT, you usually don't have any convective contribution. You just have purely diffusive correction.
Yeah. MFT is purely diffusive. You guys are purely ballistic, but you could imagine both, right?
Yeah, you can also include diffusion correction in principle, but that's going to be like one group correction or something like that, right? You cannot. I mean, it's a kind of, you have to expand around the saddle point, which we haven't done. So, but in principle, you can probably do it. All right. So yes. So yes, and then you can just solve these BMFT equations and then plug these solutions to there, and you can get them from lambda. Anyway, I didn't do the calculation. I can just tell you that you can solve these equations for these models because they are simple enough, and you end up with this kind of cumulative function. As soon as you get this expression, you realize that these cumulants are divergent because of this presence of the absolute value of lambda in the expression. So these cannot be quite well-behaving cumulants, and in general, cumulants are going to diverge in time. I mean, high enough cumulants. And why does this happen at all? And this is kind of simple to understand. It's simply because there's a normal mode, B, that propagates along the ray now. So because of this presence of normal mode with a zero velocity, there's a proliferation of fluctuations along these x equals 0, and which happens to be also the ray along which you count the number of particles that are passing along this ray. So that's why the current correlational functions defined along this ray are going to decay somewhat slower than usual, and therefore you have this kind of divergence of cumulants in general, and therefore lambda has this somewhat singular behavior. And this kind of behavior is prevented in generic systems like harmonic chains because of essentially because of their absence, because of the presence of self-interactions.
Excuse me, so here you are solving the effective Eulerian hydrodynamic equations, is it?
Yes.
And how information coming from the microscopic model?
Yeah, yes, thank you for the question. So the microscopic information is really coming, included in this so-called Jacobian. So this is basically the derivative of the current with respect to density. Yeah, so that's or even simpler for this model. Basically, you just need to know how this v velocity is dependent on this density, and that's the kind of information you need. And then you can write down these equations and so on. Right, so that's the situation for the large deviation, and now let's come to the typical fluctuations. Which, how much that time?
15 minutes.
15 minutes. That'll be enough. So this is more interesting. Now, typical fluctuations are a bit different from large fluctuations because the magnitude of the current, fluctuating current, is now set by the dynamical exponent. So this is going to be the magnitude of the current, and which can be inferred from this two-point function of the current. And now I want to understand the probability distribution of these typical fluctuations. So I'm going to define this rescaled probability distribution like this, and I want to normalize this probability, so I have to also define in this way by multiplying this time to the z in front of it. So that's the kind of object I want to compute here. Now, of course, typical fluctuations are quite different from large fluctuations in general. But in integrable systems, or in general in linearly degenerate systems, our claim is that things are pretty similar, as in large fluctuations. So what happens is that even at typical scales, there is no dynamically generated fluctuations that contributes to these dynamical typical fluctuations, but you can just again propagate your initial fluctuations at diffusive scale according to this Euler hydrodynamic equation. So that's the kind of main idea. So the situation is very similar, I'd say, to large deviation case, large fluctuation case. You just need to rescale everything according to the scale you're looking at now, which is diffusive scale. So how do we do it? So let's take gamma equals 0 limits. This is the deterministic limit. So in the stochastic charged cellular automata, in this case, there's no normal diffusion, so the system is really integrable. So, and this is kind of simpler. So let's start with that case. And now you have to, like in the previous case, you have to start use some kind of fluctuating variables. But the way you rescale your coordinates is a bit different. Now you have to put tau to 1 over z instead of just tau, because that's the scale you're looking at. And then you would say that initially these initial fluctuations, density fluctuations, are given in this way, where delta rho is a Gaussian correlated variable. This is expected to be valid at large tau. So that's the kind of important claim here, which we didn't quite prove it, but that's a well motivated assumption here. Anyway, so with that, let's look at.
Sorry. Yeah. Okay. Here, I respond. So what is the rho I? Is the typical density or the average density?
So you know this is microscopic density, right?
Oh, yeah. The question below.
Yeah. This you just take a 0. T equals 0 here.
No, the first step, like.
Sorry. Yes, this is the background density.
Background, you mean?
You have a.
Average.
No, it's just average, right? It doesn't depend on the scale, just average.
And the saddle and the typical one, the saddle point one is.
You mean the second one?
So delta
This is a fluctuating near this average, background average, on the typical scale. That's what I mean by this. And the way this fluctuate is controlled by this variable, which is Gaussian distributed. Okay. Yeah. So that's what's happening, and with that, we can take this p equals 0 half filling and look at the charge fluctuations. I wouldn't be interested in the fluctuations of the left or right universe because they are very simple and they're going to be still Gaussian, but we can still apply the method I'm going to explain to you also to these cases. But anyway, let me focus on charge fluctuation. Now the fluctuating fields have to be scaled with the z equals 2 because that's the dynamic exponent of this transport. So you have to rescale like this. So that's the your fluctuating variable, and your initial condition is accordingly like this, where delta rho is Gaussian correlated like that, and the magnitude of it is set by the susceptibility matrix. Now they are again transported by the Euler equations. So for the left and right movers, you have to do it like this. So this is the evolution of the fields, which can be, of course, easily solved like this. For the charge equation for the charge, it's a bit more complicated, but you can use the method of characteristics, and you can also claim that at large tau, the only characteristics that is going to enter into the solution is that emanates from x equals 0. So this characteristic line is really starting from the x equals 0 at t equals 0. Okay, so this is the sort of approximate solution, which of course becomes accurate as large tau, but this is the solution of this equation, where this characteristic line is given in this way. Okay, so this is the solution of the delta rho at x and t. Now you have to put that in the path integral again. Okay, before that, the total time integrated charge current is, on the typical scale, is given in this way, using this expression. Okay, so with that, you can write down the functional integral for the generating function again like this, which has this nice Gaussian integral form. And it's easier to go to the normal modes, so you have to go to the normal modes with this kind of transformation. Anyway, I have to give you the definition of this rotation matrix R, it's not important. And I just tell you that at the end of the day, what happens is that you end up with this kind of path integral over this n bar. The n bar is defined in this way. So taking the difference of these charges on the right-hand side and the left-hand side. Sorry, I didn't define what I mean by n1 and n1 and 2 are basically plus n plus and minus. I mean the charges of the right movers and left movers. Anyway, so this is what you wind up with, which you can actually calculate exactly like this. And then if you put that in this here, then you can get this probability distribution, and you can, as a result, compute this typical fluctuation, a typical probability distribution, which you see here. And this is quite anomalous, because usually you don't have this kind of second term, but you just have this first term. Also, there's no kind of square root here. So this is usually just a Gaussian, but I meant usually you don't have this term. But here you have this kind of very strange structure, which amounts to a very skewed profile of this probability distribution. I will show the profile later, but this is going to show to look quite strangely around the edges. Anyway, from this discussion, what we could learn is that depending on whether you are half filling or not, the kind of fluctuating fields that are responsible for these typical fluctuations are different. So at half filling, you just observe that only charge fields are going to be important for the determination of this generating function. And that's why charge fluctuating fields densities are the only kind of densities that are going to contribute to this typical probability distribution at half filling. And because they are transported by this nonlinear equation, this initial Gaussianity is broken by the time evolution, and therefore you end up with non-Gaussian profile of the probability distribution. And this is completely different from this the case where the system is away from half filling. In this case, you can show that the contributing fluctuating densities are the left and the right movers. And they are, like I showed you, transported by this very simple linear equation. And that's why the initial Gaussianity is kept intact in the dynamics. and you end up with a very simple Gaussian profile of this probability distribution, which I haven't written down, but that's what you can get by this kind of argument. Okay, now let's come to, okay, before going to this inclusion normal diffusion, I can also, let me also say that you can use this kind of approach to compute the diffusion matrix as well. So this is a definition of the Kuhn formula, and by using these kind of fluctuating fields, you can get this, and as a result, you end up with a diffusion constant. And this is simply because diffusion, from convection in integral systems is really coming from the other hydrodynamics, and that's why you can determine this by just this kind of consideration. And this is a priori also possible for generic interval systems. All right, now let's come to the inclusion of normal diffusion. In general, you have gamma larger than 0, so that would induce some kind of normal diffusion. And then you would ask yourself, what should I do with the previous argument? Actually, there is a nice way of getting around. So you have diffusion from convection from the previous case. Diffusion from convection still coexists with the normal diffusion, but you now have to put the normal diffusion somewhere in the equation for the fluctuating fields, and it's just you just put just like this as a fixed law, and then you also have to put white noise just to ensure the fluctuation. And this white noise is this way, and that's it. That's the kind of evolution equation for the fluctuating field. And that's what you have to do. And now this left and right maneuvers are unaffected by the normal diffusion, so you can actually show that there is no contribution from the left and right moving density. And this is going to be just a question for the charge density only. All right, so and another important remark here is that this charge diffusion matrix that you put in this fixed law is not actually a bare charge diffusion matrix, but it's a projected one. So you have to subtract the contribution from the diffusion from convection, just like this. And this expression for the full diffusion matrix can actually be not obtained by this BMFT-based approach. So this is some information that you need to feed from microscopics, which was recently obtained in the paper by Giga, which I probably cited somewhere later. But anyway, yes, in this paper, that was obtained. So you have to feed that information. But you just obtain this bit from the previous slide. So you have to compute this projected diffusion constant, and that's the kind of constant you have to put in the equation. And likewise, the Onsager matrix is also projected to be and then you can do the same kind of analysis, assuming that tau is large enough. You just solve the equation approximately like this. Well, it's quite correct at large tau, but this is the solution anyway. Where GT of x is the Gaussian kernel. And then you also can write the time integrated current like this, okay? And then you end up with just a single variable integral. I'm skipping all the details, but you need to trust me that we can do this, really play the same game as before, and you just end up with this kind of single variable integral with this PLZ defined in this way. So this is really exact. I mean, I haven't made any approximation really in this computation, and nicely enough, this is going to really be exactly the same as what you get from the microscopics. So you can get this probability distribution for generic value of gamma, where U of U looks not simple enough, and P is here. And if you plot, if you compare this against the numerical simulation, then it's theory on top. So this is a deterministic limit, and this skewed behavior is what I meant by the very unusual structures. It's really highly non-Gaussian. But then as you turn on the stochasticity, this skewedness is smeared out, and you see this rounder tip here. So this is what happens if you include the normal diffusion, which you need to do generically if the gamma is not 0, because the stochasticity is present. And the recipe here I provided is expected to be generic for any linearly degenerate systems. All right, so let me just conclude. I just used these models as a toy model for the for the system where the normal diffusion and the diffusion from convection coexist, and you can characterize large fluctuations using the integral formulation I outlined, and you can also use the same BMFT to similarly a kind of approach inspired by BMFT to correctly reproduce the typical fluctuations. And it would be interesting to find, for example, Hamiltonian systems that have both diffusion mechanisms and work with these people to really apply this method to characterize spin current fluctuations in the full-fledged XXE. Anyway, so thank you for your attention.
Thank you for the nice talk. Are there any questions?
So this coexistence of normal diffusion and diffusion you only find with stochasticity?
I don't think so. There should be a deterministic model where these two mechanisms coexist, but I just haven't found. This is a nice way of interest.
I mean, maybe that's a follow-up, but we do have examples of Hamiltonian systems with both already, right? Like, for example, just Dirac-Fried was one, but like just a Galilean gas in 2D. With two colors, you give colors and you define this as a charge, relative color. It will have that mechanism and will have normal diffusion as well. It's a chaotic system.
That's nice. And did you check that they are also linear degenerate?
I mean, yeah, we have the hydrodynamics and it's the same as the
oh, that's great. I say, sorry, I haven't.
Yeah, we studied it numerically and we sort of looked at these cumulants and they scale anomalously like you said.
I see, that's great.
It's entirely Hamiltonian. There's no.
Okay, that's good to know, thanks.
Any further questions, comments?
No, but so I don't. Okay, I mean, what is BMFT? Is really BMFT needed in what you're doing? Because it seems to me that you're just like looking at typical fluctuation on top of the average state.
Yeah.
That's not what you do. In BMFT,
that's what I do.
You take the saddle point. I mean, there is a difference between average and there is no saddle point, right?
There's no saddle point. You have to do this full-fledged path integral, but I think it's important to do this because that's the only way, at least I can think of, that allows you to keep the nonlinearity in the equation. Right? You have to. It's really important that you keep this nonlinearity. You cannot, if you do linearization of it, you get completely different things. So you have to know how to propagate your fluctuations according to this.
Of course, but if you go to the next slide. I mean, what you're doing is basically you're saying, okay, I have some fluctuating field where I put just the quadratic fluctuation, which is the susceptibility, and then I exponentiate the delta function that give me the evolution. That's not, I mean, BMFT is more than this.
Yeah, I know, but this works anyhow. So.
Yeah, no, I agree, but
I know BMFT is more than that because it was not just about diffusion.
I mean, why can't you do this on top of the, because in principle you could do this on top of the typical fluctuation of BMFT, right?
I think it's possible, yes, but this is a bit more transparent. You don't have to deal with these, if you look at this equation, this is just a vanilla Euler equation, and you can just use it.
So what I mean is that this is only for linear spools, right?
It's not linear spools, it's fully nonlinear.
No, but you're expanding around the average density.
Yeah, so in that sense, yes.
Well, it's not linear response, right? Because he does account for the nonlinearity. I mean, it's rho plus delta rho, but in the x, dx dt is large. I mean, it's normal, it's not small. But it's a different scaling from BMFT. That's the main difference. Right? He scales within the diffusive. I mean,
no, I agree, but this should be a correction on top of BMFT, right?
Yeah, I mean BMFT in the linear ballistic scaling of BMFT, that type of thing would be one of real corrections. Right? Yeah. It's a different thing. But here he scales that there, and then you get exactly what's happening there.
Yeah, because there is no other dynamics, because it starts from a flat state.
And you have to do any sort of point
yes, that's
around it, so that's better, I think.
Okay, I think it's good time to stop. So let's thank Takado again.